Hi everyone, I'm going to give you a little discussion about the dehydration of 4-methylcyclohexanol. That's going to be our first experiment. Okay, so this is the reaction. That means we have methylcyclohexanol. So this is methyl. In fact, this is 1, 2, 3, 4. 4-methylcyclohexanol. In the presence of a catalyst, we are going to do a dehydration. Dehydration means a removal of a water molecule. So in this process, we're going to lose a water molecule and we're going to get an alkene. And the alkene is going to be, you can start numbering alkene from here, 1, 2, 3, 4. That is 4-methylcyclohexene. Okay. So if we do this reaction in the lab, so we will be performing the dehydration reaction, and then we will learn how to safely work with concentrated acid solution. As you can see, this reaction happens in the presence of an acid catalyst. Also at the very end, we're going to perform a bromine test to confirm that the alkene product was formed successfully. Okay. Okay, so this is our reaction. And let's look at the general mechanism for the formation of alkene from an alcohol. Okay, so this mechanism is in your handout. Dehydration is an example of an elimination. Elimination is removal of a molecule. It could be an acid molecule like hydrochloric acid, or it could be a water molecule. Then we call it as a dehydration. Elimination occur by either E1 or E2. E1 is a unimolecular elimination. E2 is the bimolecular elimination. And this is basically the rate determining steps that tells us whether it is E1 or E2. E1 is more likely to occur with secondary and tertiary alcohols, meaning after formation of the carbocation E1. E1, SN1, excuse me, they go by formation of the carbocations, whereas E2 doesn't form a carbocation. Primary alcohols mainly undergo E2 mechanism. Now let's see how the mechanism going to take place. Now alcohol is not a very good leaving group, because if it just falls off, it becomes hydroxide. Hydroxide is a very strong base, so it's hard for us to remove OH as hydroxide. Okay, so because of that, what we do is we always going to protonate the alcohol. In order to protonate, we need to have an acid catalyst, a strong acid. Phosphoric acid, concentrated phosphoric acid is going to be our acid catalyst. So the alcohol group is going to grab a proton from the acid functional group of the phosphoric acid. So there are 3 OH groups on phosphorus. So any hydrogen can be grabbed by this oxygen and become a protonated alcohol molecule with a plus charge. Now, once this protonated alcohol is formed, when you lose or when you break this bond between carbon and oxygen, it's just a water molecule that we are dropping off or leaving. So water is a neutral molecule, so it's stable molecule. So falling of a water molecule is quite feasible compared to just leave a hydroxide groups. It's not going to happen. Okay, and then once one hydrogen is left, so this is going to be the conjugate base of the phosphoric acid, a phosphate anion, H2PO4 anion. So that is going to now act as a base. So now the carbocation is formed. So this is a E1 mechanism, and in fact formation of the carbocation, is that the rate determining step? Okay, anyways, so in the next step, what's going to happen? Conjugate base of the phosphoric acid going to grab this hydrogen, not any hydrogen on the same carbon as the carbocation, but the next carbon carrying hydrogen. So this is going to take this hydrogen, but the 2 electrons in the bond between hydrogen and the carbon is going to give to form a pi bond with the 2 carbons. and we just form the alkene, and then the phosphoric acid regenerated. So the function of a catalyst is not to used up by the reaction, it's going to regenerate at the end. So we started, it's been used up in the reaction, but then at the end it's going to regenerate it. So it has done its catalytic function. Okay, so that is the mechanism. Now let's see how the mechanism for our reaction, that this is what we're going to be doing in the class. Okay, now we have again we also have alcohol functional group, OH. Now tell me what's going to happen now. So our acid also going to be phosphoric acid, H3PO4, and then one of the hydrogens from phosphoric acid, PO2, O3, and then two hydrogens. Let me redraw this one in another form. Okay, so you had seen the phosphoric acid in the previous slide. So I'm going to separate them into H plus and H2PO4 minus. So one of the acidic hydrogens is going to grab by the hydroxyl group, and this is our catalyst. And then you're going to have a protonated alcohol. Once the alcohol is protonated, this can fall off because now we are going to generate a secondary carbocation, and also we have a good leaving group, that is going to be our water. Okay, so once the water left, we're going to have this methyl group with a positive charge on that carbon, and then the conjugate base. So there we can have hydrogen here, also you have hydrogen here. Now any of these hydrogens, because it's a symmetrical molecule, doesn't matter. So the next part is conjugate base, H2PO4 minus, going to go and grab this hydrogen, give its electron to form a double bond, and you're going to form our product, this. So that is the mechanism for the formation of methyl cyclohexene, 4-methyl cyclohexene from 4-methyl cyclohexanol, which is pretty much the same mechanism as here, but now we applied it to the product reaction that we are doing. Okay, so again dehydration requires acid catalyst, and that catalyst that we use is the phosphoric acid. And one requirement for this reaction is that we have to use an acid whose conjugate base is non-nucleophilic. Conjugate base, our conjugate base is phosphoric acid, which is non-nucleophilic, but it is basic enough to take the hydrogen and form the alkene. Okay, and that is necessarily important to ensure that the carbocation undergo elimination instead of a substitution. Okay, if it become a nucleophile, it can substitute onto this carbon and give us a substituted product. So being H2PO4 minus, it would not substitute to this carbon and give us the substituted product. Okay, normally we can also use sulfuric acid, but we use phosphoric acid. And we also use the concentrated acid, it's not the diluted one. So we use phosphoric, the highest concentration available. Okay, and also you can see here that this dehydration process, this is reversible. The forward reaction is the formation of the alkene, and then the reverse reaction is in the presence of water, it can go back to our initial alcohol. Since water is a product, because we are generating water from this reaction, I forgot to write the water. You see, it's going to be water. So this molecule, water molecule, falls off. If the reaction were attempted using a dilute acid instead of a concentrated acid, we can look up the Le Chatelier's principle. It tells us that the equilibrium would shift towards the reactants since the amount of water present is greater in dilute acid solutions. So if it use a dilute solution, so then we would see more of the reactants are being formed instead of the formation of the product. Okay. And you can also see the catalytic action, the hydrogen that we used to fall off the water molecule is regenerated at the end. So you can see that how the phosphoric acid acts as a catalyst. So since one of our products is going to be water, and as the more water is being formed, the acid is going to dilute. So what we're going to do is we need to make sure that the reaction will proceed forward. So in order to achieve that, as we distill our product, we going to as we form the product, instead of keeping the product in the vessel itself, we're going to distill it off of the reaction mixture. So the alkene and the water will be removed, and according to the Le Chatelier's principle, as the product is being removed, forward reaction will take place to compensate the loss of the products. Okay. And then what we're going to do is, after we collect, we're going to do a workup, meaning to isolate our product, and then we dry the product with magnesium sulfate to isolate the product, and we will do a gas chromatograph. Okay. Also, we can control the temperature of the distillation just to make sure that our alcohol will not be distilled along with the product. So this is how the experiment is going to be done. Here we have a heating mantle. So most of you may have seen this apparatus when we did the fractional distillation for organic chemistry 1. So this is the distilling pot, which is your round bottom flask, and this is going to be your heating mantle, heating source. You have a round bottom flask, and then you're going to be putting a column without any packing, because we want our product to distill over, okay, through the condenser. So just to make sure that it would all the vapor will go through the column and reach the condenser, we will not put any packing materials inside the column. So we're going to heat it up. As we heat it, we're going to let the reaction proceed using 150 millimoles of methyl cyclohexanol. So how do you convert 150 methyl cyclohexanol to milliliters? Because methyl cyclohexanol is a liquid. So we need to know how to convert millimoles to milliliters. So if you start with 150 millimoles, you can convert it to moles. 10 to the power 3 millimole equals 1 mole. 1000 millimoles equals 1 mole. So basically 150 into 10 to the negative 3 moles. And then we need to convert it to grams, right? In order to convert that, we need to know the molar mass of methyl cyclohexanol. So 1 mole of methyl cyclohexanol is the molar mass, which is 114.2 grams. And this is, normally we use the mass for the solids, but we can use the volume in milliliters, but then we need to use and convert it to the volume in milliliters using the density. Density is 0.914 grams 1 milliliter. Okay, that would give us 18.74 milliliters. So you're going to be using 8.74 milliliters of cyclohexanol, and then you put here, and then you will also put 5 milliliters of phosphoric acid as your catalyst, and then you're going to put some boiling chips, and then make sure you grease the joints when you set it up, and then you're going to heat it. As you heat it, and you put a stir bar also inside, so the reaction is taking place. So you are making methyl cyclohexene and water, and you heat it. As you heat it, methyl cyclohexene and water will go along the column, and then it reaches the thermometer, so we can monitor the thermometer, and we want to make sure that we keep the temperature below 120, because we don't want to distill our alcohol. We want to keep the alcohol in the flask. We only want to distill methyl cyclohexene and water. So water boiling point is 100, and methyl cyclohexene boiling point is 104. Methyl cyclohexanol, our reactant boiling point is 173. So we want to make sure that we monitor it. It would not go over 120. So we keep it under 120. And then the vapor will go through the condenser, and then we can collect it in the other side into a graduated cylinder, and we can, or you can use a beaker, or maybe you can use another round bottom flask. It doesn't matter. So you can collect. Okay, so the water and your methyl cyclohexene will distill together, and you all know that we need to put the water in the condenser. This will be water in from the sink, and this is the water out, water in from the tap, and water out to the sink. And then here you can put a thermometer to monitor the temperature. Okay, that's how we're going to perform our reaction. So after the reaction is done, what we're going to do is we're going to collect our sample, and then we're going to put it into a separatory funnel. You put into a separatory funnel, make sure the stopcock is closed, and then you add 10 milliliters of water to wash our cyclohexene and water together. Okay, you're going to be adding 10 milliliters of water, and then you swirl it with the stopper off, and then you put the stopper next, and then you're going to briefly shake it. Okay, you add water, not only with water, but I forgot to tell you, you have to put your product also here. So you will have 2 layers together. And then you put, without putting the stopper, you're going to swirl it around. And then your bottom layer is going to be aqueous layer. And then the top layer would be your alkene or your organic layer. Because the aqueous water has a density about 1 and alkene is about 0.8. So water layer would be the bottom layer. And then you're going to remove the bottom layer to a beaker and keep the alkene layer inside the separatory funnel. And to the separatory funnel, after you empty the aqueous layer, you're going to be adding sodium bicarbonate. Okay. So why do we add sodium bicarbonate? Because remember, we are doing this experiment in the presence of a phosphoric acid. And if you try to keep it like that, so your alkene layer would still have some phosphoric acid in it. So we want to neutralize it. So sodium bicarbonate and phosphoric acid will take place acid-base reaction. So you're going to be forming sodium phosphate, carbon dioxide, and water. And you have to put your stopper, and then you gently vent it and you shake it. So making sure that you vent it several times, because you are generating carbon dioxide, water, and sodium phosphate, Na2SO, sodium phosphate. Yes. Okay. So you have to do that. So after you do that, always your aqueous layer is going to be the bottom layer, and then you take the top layer, which is going to be your alkene layer, you're going to take your alkene layer, so you wash it with sodium bicarbonate. Now you have your alkene layer, which is the top layer. You're going to collect it into a beaker. You're going to empty it into a beaker, and then you're going to be adding a drying agent. Now what is a drying agent? Now since we had water and then the sodium bicarbonate, our alkene layer could contain some droplets of water. Just to get rid of that, you're going to be adding a drying agent. Sometimes we add magnesium sulfate, sometimes we add sodium sulfate. What's the drying agent we're going to be using this time? Dry the layer with magnesium sulfate, yes. So we're going to be using our drying agent, magnesium sulfate. So when you add drying agent, you will see some powdered magnesium sulfate. So you need to add it until all the clumps formation is over, and then some free magnesium sulfate will stay on the bottom of the beaker. And then you know you have added enough, and then you're going to filter this organic layer through fluted filter paper and then collect it into another beaker or in a graduated cylinder, so you can identify how much product that you had made. Okay, that's going to be the actual yield of your experimental product. Actual yield, you're going to put it into a graduated cylinder. Okay. Excuse me. So that is what we're going to be doing for the experiment. And then after experiment is done, we're going to be running a GC, gas chromatogram. Okay, so for the GC we're going to be running the GC for the product as well as for the initial alcohol. So gas chromatogram is something like that. You have x-axis and the y-axis. So in the x-axis you have the retention time. Retention time means once you inject the sample into the GC, it will take some time for it to come out. Normally the retention time depends on the boiling point of the products and the reactants. So we can run one sample and it would come at a certain time. So it would be maybe around 0.8, let's say 0.8. And then so you have another one that's coming around 0.85. Excuse me. So 0.85 is going to be a higher boiling point compared to the 0.8 retention time. Because the higher the boiling point, it will take some more time in the GC and would come up at a longer time. Okay. So we're going to use the same concept when we are trying to identify our products through the GC. So cyclohexene has a lower boiling point and cyclohexanol has a higher boiling point. So separately we inject the samples to the GC and then we can compare the two GC spectrums and see if our final product and the initial products are different, and it's going to give us the known retention times for the known compounds. Okay, so that's how we're going to compare the GC data. And also we're going to be doing one more experiment just to make sure that we have made our product. So that experiment is you're going to react these two with bromine. So when you add bromine, bromine is a brown liquid. Nothing will happen with cyclohexanol because there is no place that the bromine can add. But so the color of bromine would stay as brown, but for the cyclohexene, methyl cyclohexene, when you add bromine, so the bromine will add on to the double bond and the color of the bromine will disappear. It would become clear. So if we can see these observations, then we know that our cyclohexanol had converted to cyclohexene. Okay, that's how we're going to analyze it. Okay. And let's see what else is there for me to tell you. And you guys have some pre-lab questions. That's pre-lab question 1 is draw the mechanisms to explain the reactions below. Indicate whether each reaction is occurring through an E2 or E1 pathway. So E1 or E2 pathway. Okay, go back. So the first one is this, bromine. with hydroxide forming this. Now, what do you think is the mechanism going to be for this one? Excuse me. Now we have a strong nucleophile. So since hydroxide is a strong nucleophile, so it can go and grab the hydrogen as a base. It's a strong hydroxide. Sorry, hydroxide is a strong base. So it's going to take this and leave bromide. So this is a E2 mechanism. Okay, because in the rate determining step, hydroxide attack and also the leaving of the bromine takes place at the same time. And the next one, you have a bromine and now you have methanol as your base. Methanol is a mild base, very weak one. So you would not go and grab a hydrogen just like the hydroxide did. Instead, the bromine will fall off because this is a secondary carbon. So the secondary bromide will form a secondary carbocation. And then the methanol can go and grab a proton and complete the formation of alkene plus a protonated alcohol plus the Br minus. So later on the bromide can go and grab the hydrogen and we can regenerate methanol and HBr. Okay, and then the next one, you have cyclohexanol, and what we have is H plus and heat. Now this will take the same mechanism as we did for our cyclohexanol, which is this is going to take the hydrogen and form a protonated alcohol. So since hydroxide is a terrible water leaving group, it's going to form a protonated water molecule, protonated alcohol, and then this can leave, generating a carbocation plus water, and then even the water can act as a base, take the hydrogen and form the alkene and plus H3O plus. So the catalyst regenerated, forming the alkene, and this is going to be E1 mechanism. What about this one here, the previous one? This is also E1. Okay. Right. And then there is a question asking, excuse me, in this experiment hydroxide converted to a good leaving group. What has to be done in order to convert the hydroxide into a good leaving group? We talked about it. What we did in our experiment is we added an acid catalyst, which is phosphoric acid. Okay, so you can talk about that. And then it's asking briefly explain how we will take advantage of Le Chatelier's principle to promote the product formation in this reaction. That also we talked about it. It's in the introduction section also, or the background, you can refer to that. And then determine the theoretical and percent yield for the reaction. And draw the mechanism that explain the formation of the product, which also I did. So let's look at how to calculate the theoretical yield. So our reaction is 4-methyl cyclohexanol giving 4-methyl cyclohexene. So that's a 1-to-1 reaction. 1 mole of methyl cyclohexanol will give you 1 mole of 4-methyl cyclohexene. Okay, like this. So it's a 1-to-1 reaction. So we started with 150 millimoles So we will also should be getting 150 millimoles at the end. I will show you how to calculate the theoretical yield. So if you start with 150, I'm going to convert this into moles, 150 into 10 to the negative 3 moles. And then the molar ratio, so that's moles, cyclohexanol, and then the molar ratio is 1 mole cyclohexanol give you 1 mole cyclohexene, and then you use the molar mass. The molar mass is 1 mole cyclohexene is the mass of cyclohexene, which is 96.2 grams. And then since it's also going to be a liquid, you can convert it to milliliters using the density 0.801. So 0.801 grams is 1 milliliter. So this will give you theoretical yield of cyclohexene. And then the percent yield is going to be actual yield over theoretical yield, and then times 100. This will give you the percent yield. So you should be able to calculate the percent yield like this. Actual yield you should be able to get from your experiment video. Okay, so that's about the experiment 1. So now you should be able to answer all the questions and also do the mechanisms for the pre-labs and the post-lab. Okay, bye-bye.